Alright, this is chapter 4, properties of matter, video reassessment. Alright, so the question is, a wire made of an unknown alloy hangs from a support in the ceiling, picture right here, and then you measured the relaxed length of the wire to be 4 meters long and the radius of the wire to be 0.0005 meters. When you hang a 500 kilogram mass from the wire, right there, you measured that it stretches a distance of 3.6 times 10 to the negative 2 meters, which is delta L. Alright, so the first question asks, if you treat the wire as a macroscopic spring, what is the overall stiffness of the wire? Alright, so first, this is my diagram right here. This is 500 kilogram mass block, or whatever you want to call it. It's right there. And then so this distance right here is 4 meters. That's L. And then the radius of the wire is given right there. And then that's how much the wire stretches. So this is your initial, and then you could find your like how much your final stretch of it by subtracting that, but we're not doing that because it gives you delta L. Alright, so this is the forces acting on this block. You got the spring pulling up, and you got the mass and the gravity pulling down. And right now it's at 0. And this is the equation right here for the spring. But so right now we have the forces equaling, they equal 0, and it's only going in the y direction, so no need for the vector. But it's only going, I mean, we could put the vector, but the vector would be 0 comma, and then we'd have fs equal mg or whatever. So we're not going to write it in vectors. Alright, so right now the forces are equal because the block isn't moving. It's stopped. It's not moving. Alright, so then we got, right here we're showing to equal each other. So what we're going to do is we're going to let mg take the spot of fs in the equation. So then we plug in mg right here for fs in the equation, and then we get mg equals k delta L, and k is what we're looking for. So then we just shift the equation around, and then we get k equal mg over delta L, and k is just the stiffness of the spring. Alright, so then we plug in our values. K equals, so our mass is, the mass 500 kilograms, and then we get the gravity's 9.8, that's the constant, over delta L, and delta L is given right here. Alright, so then we plug that in the calculator, and this is what we get, newtons over meters. If you can do the units by yourself, they cancel out, and it's newtons over meters. Alright, and then so B is, what is the value of Young's modulus for this alloy? Alright, so then Young's modulus equals stress over strain, so equals, this is the equation right here, stress over strain. Alright, so then we're going to write down everything we've been given. So F equals 500 kilograms, and then A, which is equals the area, is the area the spring is, and the spring is not the spring, the wire is like this. I mean, obviously it's bigger, but that's like what the wire looks like. So it's a cylinder, or it's a circle, because we have the radius or whatever, so we need to find the area. So pi r squared equals, and then so we take pi, and then we take our radius, which we got up right here, and then we square it, and then that's what we're going to get it for the area. And then we got delta L, which is given to us right there, and then L naught, 4 meters. We got that. Alright, so then basically we just take all this that we already have, and then we plug it all into the formula, and once again take care of our units and stuff, and this is what you'll end up getting, 7.07 times 10 to the 10th newtons over meters squared. Alright, and then the last question asks, using Young's modulus, identify that what the wire is made out of, and just look up what metal has this Young's modulus, and you figure out that it's aluminum. And that's it.